Now that we've talked about an intuitive understanding of acceleration in 2 dimensions, we're really well set up to think about circular motion. And circular motion has a lot of applications in medical equipment. I'll talk about centrifuges. It has some physiological effects. And then later, when we start getting into rigid body motion, and we'll be able to start talking about a lot of biomechanics. There's a lot of applications to circular motion and understanding the biomechanics of limbs moving. So the basic idea of circular motion is exactly the same as the intuitive understanding of acceleration. So let's say that we have an object moving around this circular path. Let's say it's going this way. And let's say, okay, so first pretend that shape is a circle. But let's think about this point at the bottom of this circular path. Let's say, just so we have something to put down here, that it's slowing down. So the rotations are slowing down. Well, how would we think intuitively about the direction of acceleration in this case? We know that the velocity vector is tangent to the path, so it would be this way. We know that it's slowing down, so the parallel part of the acceleration has to be opposite the velocity. And then last, we have to figure out which perpendicular direction to these is the object turning. It would keep going straight along this straight velocity line if it wasn't turning. So we know it has to be turning, and the direction it's turning is this way. With a circle, you can just always think of it as toward the center of the circle. So here's our A perpendicular. And we already understand all that. One thing that is going to be different here, and I mean, I don't get to make these rules, but when you're talking about circular motion, you give these a different name. So I want you to get used to these names. This parallel part of the acceleration is now called the tangential acceleration. Well, that makes sense because that is tangent to the path. And this perpendicular acceleration is called the centripetal acceleration. Well, that makes sense if you know what centripetal means. It means toward the center. That's, I mean, no one knows that until they take physics, but both of these make sense. You have one of these accelerations that's toward the center of the circle and one of these that's tangent to the circle. Okay, so I'm going to list out really the only 3 new things that we have. And 2 of them are this thing that I've already told you about, the new names. So there are only 3 new things to us. And 2 of those are just new names. Well, the first one is that for circular motion, the parallel acceleration is called the tangential acceleration. And I'm going to always write it like that. So in words, it's the tangential acceleration. Okay, so the first name is out of the way. Now the second new name for circular motion The perpendicular part of the acceleration is called the centripetal acceleration. And so we're going to use these two names. If you're saying this in words, this is centripetal acceleration. So those two are kind of, I mean, they're important for communicating with people, but they don't really change our understanding. This third one is really important, though. This is the only new thing that's anything other than a name, but this is a crucial thing. So in circular motion, the magnitude of the centripetal acceleration is always v squared over r, where v is the speed of the object, and r is the radius of the circular path. Okay, and this is kind of amazing. I mean, what it says is that no matter what's happening, if it's speeding up or slowing down, in order to maintain this exact shape of a circle, that perpendicular part of the acceleration, the part that makes it turn, has to have a very specific ratio of, you know, speed, velocity, speed, radius kind of stuff. So if your centripetal acceleration was bigger than v squared over r, it would turn too sharply to stay on the circle. It would start turning inside that circle. And if v squared over r was less than, if the centripetal acceleration was less than v squared over r, it would not be turning enough to maintain this circular path. So this is just true of every circle. And so how do you get the total acceleration? So once you know the tangential acceleration and the centripetal acceleration, then the total is just the sum of these two. Okay. There are two types of circular motion. The first is uniform circular motion. This is when the object is not changing speeds. Well, think about these two parts of the acceleration, the centripetal and the tangential. Which one of those determines the speed change? It's the tangential acceleration, because that's the one that's equal to our A parallel. And so the total acceleration for uniform circular motion, if that speed is constant as the thing goes around the circle, then this one is equal to 0, and the total acceleration is just the centripetal acceleration. The opposite of uniform circular motion is non-uniform circular motion. And in that case, you have both of these two. Okay. One thing I want you to think about before I start talking about how to do calculations is, you know, we've done a lot of problems that involve constant acceleration. Is there ever a time when circular motion is constant acceleration? Well, let's think about just a simple uniform circular motion case. The speed isn't changing. The radius of the circle isn't changing. And so if you go through the calculation of the centripetal acceleration, what you see is the acceleration is always toward the center of the circle with a magnitude of v squared over r. So is that constant acceleration? It's not, because as the object goes around the circle, the vector that points in that direction keeps changing. And constant acceleration has to have not just the same magnitude at all times, it has to have the same direction at all times. So circular motion is never constant acceleration motion, and you can never use those constant acceleration equations for circular motion. So let me just get that in here. Remember, circular motion is never constant acceleration. Because in every case, the direction of the acceleration is always changing. Okay, so now I'm going to go through a set of steps that you can use for problems. This will work for any circular motion problem. And the first thing that we're going to do is choose a way to view this problem. Okay, so let's say that you're doing a circular motion problem and all you have, look how good I am at drawing toy trains. Okay, so let's say this train is going around train tracks on the floor like that. It's in circular motion, and we want to calculate something about its motion. So the first thing we are going to do is choose a view where the circle is visible. Okay, well, in this case, that means either a view from above or from below. I guess I would normally do a view from above. And so there's the top of the train. And we're going to take this top view. And we're also going to choose a coordinate system while we're here. The location of the origin doesn't matter, only the directions matter for the kind of calculations we're going to do. So choose the view where you can see the circle, orient the coordinate system, and that's the first step. Second, you need to make sure you have a point on the circle to analyze. It might be given in the problem, or you might just get to choose it for yourself. So in this case, if that's our circular path, that's our coordinate system, I'm going to choose this point. Third, draw the velocity vector. So if we're looking at this point, let's say that this is let's say that this is slowing down and it's going around this way. Okay. Then in our top view, the velocity, I usually use red for velocity, but I also used it for the coordinate system. So the velocity is going to be this way. Next, if it's non-uniform circular motion, then you're going to draw the tangential acceleration. So in this case, that is, since it's slowing down, that's opposite the velocity vector. Five, draw the centripetal acceleration vector. Six, calculate the magnitude of the centripetal acceleration vector. And then finally, put those accelerations together. So the total acceleration is the tangential plus the centripetal. Okay, and that's just a way that you can always use to calculate the acceleration in circular motion. Now I'm just going to go through a few example problems, and I'm going to stick to this order of steps. I think you should do that too. You just want to get in a pattern where you do it the same every time so you don't forget stuff. So first I'll do an airplane example. Let's say that we have an airplane and it's in a circular path like this. Okay, so that's supposed to be like a semicircle. And the radius of this circle is 250 meters. And as this plane gets to this point on the circle, let's call that the point P. The speed is constant, which means, you know, the speed isn't changing, and the value of that speed is 120 meters per second. And we want to calculate the acceleration at that point P. Okay, I'm just going to go through the steps. The first step is choose a view where the circle is visible. That was already given in the problem, so I didn't have to change anything about the view. Let me choose a different color for this coordinate system. So there's X, there's Y. And we want to see what's going on at this point. The first thing we do, now that we've chosen this and marked the point and everything, is draw the direction of the velocity vector. Now, if it's changing speed, we need to draw the direction of the tangential acceleration. In this case, it's a constant speed, so I'm just going to leave that off. Then draw the centripetal acceleration. That's you can see in the negative x direction. And so now we'll calculate the magnitude of the centripetal acceleration. That's v squared over r. And that is 57.6 meters per second squared. Now looking at the direction of that, if you drew a coordinate system, put the tail of that centripetal acceleration vector at the origin, and calculated the coordinates at that point, you would see that that's just 57.6 in the negative x direction. So the centripetal acceleration is negative 57.6 meters per second squared I plus 0j. You can just write it like that and just leave it off. Is that, survivable? Yeah, that's so the way people think about the accelerations that pilots are going through is through the number of, they call it g forces. It's really an acceleration, but the number of g's that they're experiencing. Well, 1g is 9.8. So this is very close to 6 g's of acceleration that this person is experiencing. And that's getting into the range where people might start having some trouble with blacking out. When the acceleration gets that high, it can, depending on the direction, it can hold excess blood in your brain, which causes certain problems. It can prevent blood from getting to your brain, which causes other problems, and they lead to blacking out, which obviously is something you'd really like to avoid when you're piloting an airplane. So that's sort of our first thought about G's in acceleration. Now the second example, I'm going to do one that's non-uniform circular motion. So let's say you're so bored you have a mass on a string and you're swinging it around in a circle. So the circle would look something like that. Okay, and let's say it's going this way around the circle. Okay, and this is, say we're looking at this from the side, so gravity is acting toward the bottom of the page in this picture. And let's say that at the point, okay, so the point we're going to choose to analyze is this one. I'm sort of choosing the same point as last time. You don't have to do that, but that's just the way this worked out, I guess. And so at this point P, the ball is slowing down at 9.8 meters per second squared. Okay, that's only at that one point in this motion that would happen, but that's what it would be here. The acceleration of gravity would be the tangential acceleration. And we want to know what's the acceleration of the ball. Okay, so first draw the path. Choose the directions of your coordinate axes. I mean, there's not much to choose. Usually you can just choose the normal 1. And then this is the point we're looking at. Now draw the velocity vector. The tangential acceleration, it's slowing down, so that's going to be opposite the velocity. And then the centripetal acceleration vector. The magnitude of the centripetal acceleration. Did I give a speed here? I need to give 2 more things in this problem. The speed, we're going to say, is 10 meters per second. And the other thing that you need to know is the length of this string. Notice that the length of this string is the radius of that circular path. And I'm going to say that that is 10 centimeters, 0.1 meters. Okay, we're assuming that that was all given. I just forgot to write that down. So the magnitude of the centripetal acceleration is v squared over r. So that is 10 squared over 0.1. And that is 100. So this comes out to be 100 times another 10 is 1,000 meters per second squared. Now from the picture, you can see that that's in the negative x direction again. So as a vector, our centripetal acceleration is negative 1,000 meters per second squared I. Now this one, we do have to figure out the vector components for the tangential acceleration. We already have been told the magnitude is 9.8. We can see that this vector is in the negative y direction. And so the tangential acceleration is negative 9.8 meters per second squared j. Now finally, just add those two together. And you get that the acceleration is negative 1,000 meters per second squared I minus 9.8 meters per second squared j. Okay, medical application of circular motion is the centrifuge. And a centrifuge looks something like this. You have a body that rotates around very fast, and inside here are places where you can set test tubes of different types. So let's think of one of these guys with the plastic lid to open. You have a sample of some kind of liquid there. You put this in these spots. You spin it around really fast. And the point of that is that it uses the high accelerations that you can get from circular motion to stratify substances by their density. And so if you're trying to get the most common uses in blood, if you're trying to isolate red blood cells from the rest of the red blood cells are more dense than the other materials. And so when you spin it around, the more dense materials will move out to the tip of the, you can imagine that this test tube is at an angle in there. And so the tip is farther out from the center of the circle than the top is, and the red blood cells will accumulate in the bottom of the test tube. So some uses that are related to biology and medicine. The first one I said is to separate red blood cells from the blood. The second thing that you can do with this is it can be used to isolate larger organelles from cells. And the third is for DNA samples, you need to get a certain fraction of your test sample to be DNA for it to be useful. Well, you can use centrifuges to concentrate DNA in your sample. And all of these work the exact same way. You put the sample in the centrifuge, you spin it, and the denser materials will move farther out from the center of the circle. And that will create layers of materials by density. If you imagine the motion of a sample from above, and let's say we're thinking about this point right here, and let's say it's going around this way. Our coordinate system isn't really going to come into this, but I'll draw it anyways. Well, we know that the velocity is this way. We're going to assume that there's uniform circular motion. We're not worried about changes in speed. And so the only acceleration that we're going to get is the centripetal acceleration. And the magnitude of that centripetal acceleration is the speed squared divided by the radius. Accelerations with centrifuges are given, so instead of just giving the accelerations in meters per second squared, they're given as a relative acceleration. And that is the number of times the g acceleration you have. And, you know, the g is 9.8 meters per second squared. The relative magnitudes the relative accelerations range from about 10,000 to 1,000,000. And what that means is 10,000 times 9.8. So this would be 98,000 meters per second squared to 9,800,000 meters per second squared. Okay, so as far as calculations go, let's say we have a centrifuge. I'll use the drawing that I just used above. So let's say you have this centrifuge, and the radius of the centrifuge is 10 centimeters. And we want to know how fast a sample has to be moving. So how fast must the sample move to achieve a relative acceleration of 100,000? Well, we can draw these parts. This question really could be answered without going through all the steps carefully if you just notice that the only thing producing acceleration is centripetal. So you're just going to set v squared over r to this acceleration. But if you're going through all the steps, it would look something like this. And now we're going to say the centripetal acceleration is equal to v squared over r, and we know what r is. And we want to set that equal to 100,000 times 9.8 meters per second squared. So we're setting this to 980,000 meters per second squared. If we multiply both sides by 0.1, we get that v squared is equal to 98,000. Or in other words, the speed, we want the positive, is the square root of 98,000, which is 313.05 meters per second.